Welcome to the AP Calculus AB video for skill number 131. I can use limits to define the derivative of a function f at a number a and use this in problems of position and velocity. And we're going to really, in this video, talk largely about the definition of the derivative. So, before we get into it, to the right we have a picture of the capital of a column in the Parthenon. And to start out our capital unit, the trivia question is, looking at this capital, we are able to determine what order of architecture is being used in the column. Alright, so we're going to learn about the derivative of a function, and we're going to use the two basic definitions of the derivative. And briefly, the derivative could be considered the instantaneous rate of change. There are some people who have learned about derivatives in their physics class or perhaps in earlier calculus classes. The important thing is we need to be able to use and apply both definitions. So before we even get into shortcuts for derivatives, we have to be able to do it the long way. The AP test will have a couple questions which rely on us understanding how to use the definition of the derivative. So I'm going to build this by working off of one of our earlier skills, which was the slope of secant lines. So let's get into it. Example 1. Find the average rate of change, average velocity, for a particle which travels according to the position function s of t equals t squared minus 3t from t equals 5 to t equals 6. So if you remember, basically average rate of change, we're looking at some sort of function that maybe does this, and we are interested in what is the average rate of change from time 5 to time 6. So a slope of that line. Alright, and we know that the average rate of change can be found by taking let's see, we wrote a f of b minus f of a over b minus a. This was slope of secant lines in skill 129, I believe. And so we do that for time 6 to time 5, and we find that the average rate of change, which in this context we consider velocity, is 8. The problem had no units, but we'll just assume that it was meters and time was in seconds. So 8 meters per second. That's example 1. That's nothing new to us. That's just kind of reviewing what we already know. We're going to try this again, except for this time, instead of going from time 5 to time 6, we want to go from time 5 to time 5 plus h. And h is some unknown value. The process is still the same. We want to find s of 5 plus h minus s of 5 on top, and then 5 plus h minus 5 on bottom. So I have written this out. This is s of 5 plus h, and then s of 5 we found was 10, so I just put 10 there. And the trick here is we need to expand all of this out. So we multiply 5 plus h times 5 plus h, and we get this value. We distribute the 3 in, and we get that. And if we simplify the numerator all out, we get 7h plus h squared. And our denominator is h, so we factor out an h. And we find that the average velocity from time 5 to 5 plus h is 7 plus h. And this kind of confirms our finding earlier. If we let h be 1, we'd be going from time 5 to time 6, and we get 7 plus 1, and that matches our 8 above. So this supports what we found earlier. We're still not quite to the definition of the derivative, but we're slowly building to it through examples. So let's take a look at the next example. We want to find the instantaneous rate of change. So instead of finding an average rate of change, we're looking for the exact rate of change, the instantaneous rate of change at that value of 5. So how fast is it increasing right there? So basically what that means is we're going from time 5 2 time, let's do this in black so we can see it better, 2 time t equals 5 plus h, where h is 0. So essentially our h is approaching 0. So what we can do is we can take the limit as h goes to 0 for our findings from example 2. And if we plug 0 into that, direct substitution yields an answer of 7 meters per second. So right at time 5, we're traveling at 7 meters per second. And this is getting at the definition of the derivative. Finally, we're going to remove one more piece of information, and we want to find an average rate of change from time t equals a, so now we don't even have a number, to t equals a plus h. And this is getting into tracking a lot of variables, but we can do this. What we do is first we plug a plus h into our function, which was x squared minus 3x. I guess it was t squared minus 3t. So we do that for a plus h, and then we do it for a, so a squared minus 3a. And expanding out the numerator, we get this long mess here, and we see that terms start to cancel. The a squared cancels with the negative a squared, the negative 3a cancels with the positive 3a, and then the h in the denominator cancels all out, and we find that the average rate of change for the same particle is this value. So if we wanted to go from time t equals a to time t equals a plus h. And just to verify our findings earlier, if we wanted to do it from time, we're going time 5, so we'd be from time 5 to 6, so our h is 1. And we get this value. We have 10 plus 1 is 11, minus 3 is 8. So this still confirms our finding in example 1. Excellent. Finally, in example 5, this leads us to the instantaneous rate of change of the same particle at time t equals a. And so our instantaneous rate of change, we're going from time a to time a plus h, where h was 0. So we're taking our limit as h goes to 0 of that function, and we find this equation can tell us the instantaneous rate of change. And if we were interested in at time 5, we'd get time 5 minus 3 gives us 7, which confirms what we found in our earlier examples. Excellent. And we have now arrived at the definition of the derivative of f at a. So the derivative of a function at the point a, or if you wanted to call it the instantaneous rate of change at the point a, is the limit as h goes to 0 of f of a plus h minus f of a over h. Further down on the page, I redefined this calling it a function, so we actually make the derivative a function. So there's very little difference between these two equations. The only difference is this is for a specific point A, and this is going to be for all values. So what we've done is we've just substituted a in with x, and we've created a function, the derivative function. So we have our function f, and the derivative of that function with respect to the variable x, which we will call f prime, is this value, provided the limit exists. And we'll get into later on scenarios where this limit doesn't exist and talk about what that means in calculus. But for now, we're just going to focus on ones that the limit will exist, just to keep it simple.
Ma. 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 Ma.
Alright, I wanted to also introduce an alternate definition, and most alt calculus textbooks will show both definitions because both of them get used. There's benefits to both of them, but for the most part, what I want you to understand is that they both yield the same idea, which is finding the derivative of a function. This one, instead of taking the limit as h goes to 0, what we're going to say is we're going to take the limit as x goes to a. And this can be understood graphically a little bit better, and I'll try to go into that in class. But when we're taking the limit as h goes to 0, we have this point, and our h is getting closer and closer to this point. And so we're closing the window of the line from the red point here to the blue point. And with this alternate definition, what we're doing is we're kind of taking our x, this is what we have a, and we're going to take our x value and slowly get it closer and closer to a. I don't want to say it's approaching from different sides because that's not what's going on, but it kind of appears as though. That is, I wouldn't stress it. What I would stress is that you learn to recognize both definitions and know how to use both definitions. So what I've done here is in example 6, I've given a function and asked you to use both definitions to find the derivative of the function at the point x equals 7. So we'll work through our first definition, which is right here. That means take the function at x plus h and subtract the function at x. So we've created that in the numerator with h in our denominator. If we expand out the numerator and cancel all the like terms, and you can do that on your own, we find that the numerator is 2xh plus h squared. And then we can take our h term and cancel it out of the top and the bottom by factoring. And we find that our limit, oops, this is a typo, this should say h goes to 0, is 2x plus h. And if h is going to 0, once we take the limit, it becomes 2x. And we are interested in the limit as x goes to 7, or at x equals 7, so we plug 7 in, and we find that the derivative is 14. So the derivative of the function at 7 is 14, meaning on the curve x squared minus 1, which looks kind of like that, all the way out here at a value of 7, the instantaneous rate of change of the curve is 14, so the slope of that line. We do the same thing in definition 2. It's just a slightly different approach. Definition 2 tells us to take the limit as x goes to a of f of x minus f of a. And so what we can do is we can plug in x squared minus 1 minus a squared minus 1. So the function at x and then the function at a. We'll see that the 1's cancel each other out, and we're left with x squared minus a squared in the numerator and x minus a in the denominator. And through the process of factoring, we can cancel the term off the top and bottom, and then we take the limit of x plus a. And that is 2a. So now we found the derivative of at a, and we're interested in a value of 7, so we plug that in, and we get 14 again. And so both of our definitions confirmed a value of 14. As far as which definition is better, I'm kind of partial to this definition. It seems easier to manipulate. This definition here, the second definition, has its merits, but it might require a little bit more advanced algebra. As you can see, we had to remember how to factor this, and if we've got like x to the 4th, x to the 5th, it could get pretty nasty. So I tend to stick with definition 1. The AP test will of course question both of them. Alright, thanks for watching this video. As a wrap up, you should be able to use both definitions of the derivative One of them is the limit as h goes to 0, and the other one was based off of the limit as x goes to a. And the answer to the trivia question is, featured to the right is a column of the Parthenon, and we can see by the very simple capital that we are in the Doric order of architecture.